Hello, Gary Parker here, Intermediate Algebra fans, and I received a special request for some information on logarithms. Let's check them out. So, what the hell is a logarithm? Good question, I'm glad you asked. Before we ask Desmos, let's ask Google. According to Google, a logarithm is a quantity representing the power to which a fixed number, the base, must be raised to produce a given number. So a logarithm is the power. Power is an exponent. So what is a logarithm? A logarithm is an exponent. They are synonymous. Logarithm is an exponent. So for example, we know that 10 to the second power is 100. What's the exponent here? The exponent is 2. So that means the log has to be 2, because a log is an exponent. Now, there's a catch. An exponent has a base, so a logarithm has to have a base. An exponent has to have an object that it acts on, so there's a logarithm. So that's the interpretation of 10 to the second power equals 100. And again, the key to this is that the word logarithm is synonymous to the word exponent. So the log has to equal the exponent. Why? Because a logarithm is an exponent. So it was an invention of mathematics made several hundred years ago. Super, super powerful. Allows us to do a lot of things that we couldn't do otherwise. Common places you see logarithms are in science. So, for example, you've heard of decibels, how we measure loudness. That's a logarithmic scale. The Richter scale, how we measure earthquakes. That's a Richter scale. A logarithmic scale. It measures changes in energy. What else? pH, how we measure the acidity of something. That's another logarithmic scale. So other places they're useful is in astronomy, because distances are so vast, we can't talk about the regular numbers. We have to talk about like what power of 10 it is in order to deal with it. You may ask, well, why would we bother talking about powers of 10? So a simple example of why we might want to talk about that is, let's put 0 here on the number line. And then over here, at the end of the number line, we'll put 1 million. And so what I want you to do is draw something similar. And then if let's not do a million, let's do a billion. Make it bigger. So if we have to go from 0 to a billion, 1 billion, where on the number line would you place a million? So I'll give you a second to think about that. Pause the video if you need to. Play around. All right, so maybe you said, let's put 1 million like right over here. Like he's a billionaire, I'm a millionaire, we can hang out together. So maybe this is where I'll put 1 million. Well, if that's the case, let's just spell million if it does, then 2 million would be over here. But 2 million ain't a billion, so that's not correct. So we gotta do that. All right, so maybe a million is like over here. Well, if that's 1 million, this would be 2 million, and that would be 3 million, and that would be 4 million, 5 million, 6 million, 7 million, and a billion ain't the same as 8 million. So again, I got another problem. Well, shit, what's the problem? Problem is, a million would actually be way over, like right about there is where I should put 1 million. And you may say, what? How can it be way close to 0? Well, think about it this way. Here's a million. And then here's a billion. Okay, doesn't look too bad. How come the million is so little? Well, the way I wrote it here, to make 1 billion, I need 1,000 millions. So that means a million is 1,000th of a billion. I need 1,000 of these millions to get a billion. So then you ask again, hey, I'm a millionaire, you're a billionaire, we hang out in the same club. The answer is no, we don't. There's no relationship between a millionaire and a billionaire. A billionaire has 1,000 times more money. Okay, so they're not in the same school. They're not in the same club. Millionaire and a billionaire are not the same thing. So powers can sometimes be more helpful. So a million, that's represented as 10 to the 6th power. A billion would be 10 to the 9th power. And sometimes it's easier to talk about the power of 10. Powers mean vast differences, 10 times greater, 100 times greater, 1,000 times greater. So we shouldn't take that for granted. But kind of gets the idea of why we need logarithms to make comparisons of numbers that really aren't that close together, but they're kind of sort of related. All right, so back to the problems you need to worry about in a class like this. The idea of an exponent, 2 to the 3rd power equals 8, related to the idea of a logarithm. Okay, so rewriting this as a logarithmic statement. First, logarithm and exponent mean the same thing. So the log has to equal the exponent. So the log is 3. Next, logs and exponents have to have a base. Here the base is 2, so here I write a little tiny 2 under the g. And then I have to have an object the logarithm acts upon because it's a function. So it's the 8 that it acts upon. So what this says, the way to interpret a logarithm is what power do I raise 2 to, comma, get 8? Answer, I would raise 2 to the 3rd power to get 8. Okay. So a logarithm asks the question, what is the power? Another example. Suppose we had 3 to the 2nd power, that is 9. Logarithm has to equal 2. Why? Because log and exponent mean the same thing. 2 is the exponent. Logarithm has to have a base, and then it has to act upon something. That's always what's on the other side of the exponent statement. Going the other way, somebody says, hey, log base 10 of 1,000 equals 3. That must mean the base is 10. A log is an exponent, so the power must be 3. So 10 to the 3rd power must be 1,000. So logarithm is a matter of just getting used to the notation. Like an exponent, a logarithm has to have a base. Technically, a logarithm is an exponent. So the log has to equal the power. And then you have the result, which is the result of the exponent or the object of the logarithm. So that's the other part of this equation. Object of the logarithm is the result of the exponent. So calculators present another problem. So there's the idea of a common log. Common log means the base is 10. So sometimes you'll see statements like log of 100 equals what? If there's no base, then that must mean log base 10. So when the base isn't written, that's called a common logarithm. It's assumed to be base 10. All right, what does this mean? Well, the base is 10. A logarithm is a power. So 10 to what power is 100? And oftentimes we can just guess. Oh, yeah, I know that. 10 squared, that's 100. But it doesn't always work that way. So for example, 10 to what power is equal to 150? Well, let's see. I know 10 squared is 100, and 10 cubed is 1,000. So the answer, that power, has to be some number that's greater than 2, but less than 3. Probably closer to 2, right? So we don't have any good means of guessing besides guess and check, but I can rewrite this as a logarithmic statement. So the logarithmic statement would be the log has to be equal to the power, my missing number. The base has to be 10, and the result of the exponent has to be the object of the log. So that means I want log base 10 of 150. Now I can plug it into a calculator. All right, calculator time. So if I go to a calculator and I just type, Desmos is a calculator. If I just type log of 150, Desmos will assume, whoa, too big, that I'm using, since I didn't write the base, that I'm using log base 10. So Desmos says the answer is 2.17609. Let's write that down. 2.17609. Oh, crazy pen. Approximately 2.17609. Now, usually, kind of like when you take square roots, it's not a nice number. It goes on forever. So I have to say it's an approximation. So what I should find if I type into the calculator 10 to the power of 2.17609, I should get pretty close to 150. So let's check that out. Calculator. 10 raised to the power, oops, wrong button, raised to the power 2.17609. Computer says it's 149.99956. Pretty close. If I round that to the nearest tenth, hundredth, or thousandth, I'm going to get 150. So it worked out. So again, logarithms are exponents. It's just a matter of interpreting the statement correctly. Now, as far as graphing these suckers, that's another challenge. It's pretty straightforward to graph an exponent. Why? Because you've been using exponents for a long time. You just started working with the idea of a logarithm. So if I wanted to graph something like y equals 2px, I would make a table for x. Like maybe I want to graph -1, 2, or -1, 0, 1, and 2. So 2 to the -1 is a half. 2 to the 0 is 1. 1 is 2. 2 to the second is 4. So quick sketch graphically. I get the point -1. That's 1. 1/2 would be about right there. And then if I plug in 0, I get 1. If I plug in 1, then I get 2. And if I plug in 2, I get 4. So 1, 2, 2, 4. Next would be 3, 8, which is way the heck up there. So an exponential curve, whoa, I missed my points, tends to go up. Sorry, magic pen is misbehaving. And then it tends to just creep down. And it's not going to cross the axis down here on the left side. Now, logarithmically, logs and exponents inverse each other. So if I needed to graph y equals log base 2 of x, two ways to look at it. One way is I can just switch x and y from over here, because a logarithm gives me the exponent. Right? Oops. X, y. So if x is 1/2 here, then the power would have to be -1. If x is 1, the power would have to be 0. If x is 2, the power would have to be 1. And if x is 4, the power would have to be 2. Double check one of those statements, like 4, 2, for example, up here. Log base 2 of 4 equals what? Question mark. And sometimes we can answer these just by thinking about it. That means 2 to what power is equal to 4? Well, 2 to the second power is equal to Oh, okay. That's where that comes from. I graph those points. What I end up with is 1/2 -1 is about there. And then 1, 0 is here. And then 2, 1 would be there. And 3, 4, 2 would be about right there. And my graph looks something like this. And whenever you draw a graph, if you miss your points, just make them bigger. That helps. And then it plummets down this way, and it's going to try and touch the y-axis, but it's never going to. It's called an asymptote. Pretty cool idea also, but I'm not going to get into that now. These are inverse functions of each other. Why are they inverse functions? Well, because the x and the y's reverse each other. All right, that's my brief introduction to logarithms. Have fun with that. Good luck. Do good math. See you in the future.